All right, welcome back. So let's talk about one of the biggest puzzles in physics, the masses of fundamental particles. If you look at them, they seem all over the place, almost random. But what if they're not? What if there's a hidden logic to it all? Today, we're going to dive into a really fascinating model that claims it can derive the mass of every single quark and lepton from just one unified set of rules. Okay, so to get into this, we're actually going to start at the end. Just take a look at this. This is the big payoff, the stunning final result of the model. It's a complete table of particle masses that it calculated, from the teeny tiny electron neutrino all the way up to the absolutely massive top quark. I mean, that is a seriously bold claim, right? So yeah, that immediately brings up the big question, the central mystery we're going to unravel here. How on earth is this possible? What's the secret sauce? What's the underlying logic that could possibly generate this entire vast hierarchy of masses from just a single starting point? To figure that out, we have to pop the hood and look at the engine. To solve this mystery, we first need to understand the basic building blocks the model is working with. It really all comes down to three key concepts that make the whole thing go. First up, we have something called generic fermions. Now, you know fermions, they're the matter particles, the quarks and leptons that make up, well, everything. In this model, you can think of these generic versions as the raw clay for all the other particles. They are the fundamental starting points, and each one is assigned a specific starting mass. So, you've got the clay. Now you need the sculptor, right? That's where scalar bosons come in. Bosons are usually the force carriers, but here they act as agents of change. They interact with those generic fermions, and depending on the rules, they can either pump up the mass or shrink it down. They're the ones that shape the final particles. And finally, how do these interactions know what to do? I mean, what are the rules? Well, that's all governed by combinatorial values, or CVs for short. Every single piece of the puzzle, both the fermions and the bosons, gets a number assigned to it. You can think of this CV as the instruction manual. It's the number that dictates exactly how the interaction is going to play out. Okay, so let's recap. We've got our ingredients, generic fermions, scalar bosons, and their CVs, which are the rules of engagement. Now let's open up the engine room and see the core formula that puts it all together to crank out those masses. This is it. This is the mathematical heart of the entire model. Its job is to create a mass factor, a multiplier that scales a particle's base mass way up or way down. So let's look at it. You see that 10 to the power of x part on the right? That's the powerhouse. It's like the sledgehammer that creates these huge astronomical jumps in mass between particle generations. And that other part on the left, that's your fine-tuning dial. It tweaks the final value with incredible precision. But here's the thing, the whole magic of this formula, everything, hinges on that one little variable, xp. So you have to ask, right? Where does this xp number even come from? It can't just be random. Otherwise, the whole model falls apart. And this is the secret, right here, straight from the source. The XP variable is calculated systematically using a really simple rule. You take the combinatorial value of your starting particle, the fermion, and you do one of two things to it. You either cancel it out to zero or you double it. That's it. Then you just add the CV from the scalar boson that's interacting with it. That simple operation gives you your XP. And check this out. This is a perfect example of how it works for quarks. Look at the formulas on the left. You can see that rule playing out right there. For the first two generations, see how the Q2CV minus Q2CV part just cancels itself out? That's the zeroing out part of the rule. But for the third generation, it's Q2CV plus Q2CV, which doubles it. You run those numbers, add the boson CV, and you get the exact X values, and therefore the mass factors, that you see in the table on the right. It's beautiful. And what's really cool is that the exact same logic applies to the leptons, they just have their own unique base CV. For them, the doubling rule applies to the first generation, and the zeroing out rule applies to the second and third. It's the same system, just with different starting numbers, which is what gives you this completely different but totally consistent set of mass factors. Okay, so we've got the theory down. We've seen the ingredients, we've looked at the engine. Let's put it to the test. Let's actually build a particle from scratch and see this thing in action. We'll calculate the mass of the heaviest known fundamental particle, the top quark. So, according to the model, the top quark is made from a generic d quark interacting with a specific scalar boson. Let's follow the steps. First, we start with the d quark's base mass, which is 200 electron units.
Then, the boson does its thing, converting it to a generic U quark and bumping the mass up to 2000 EU. Finally, we apply that third-generation mass factor we calculated a minute ago, which is a multiplier of 200. You do the math. 2,000 times 200, and what do you get? 400,000 electron units. And bam! That is exactly the value the model predicts for the top quark. And get this, every other particle mass you saw on that first slide is calculated in a similar step-by-step way.
Pretty neat, right? So now that we've seen how this sausage is made, so to speak, what does this all mean? What's the bigger picture here? If a framework like this holds up, what are the implications? Well, if this model is on the right track, it points to some really deep hidden patterns in the universe. For one, it's saying a particle's generation, whether it's first, second, or third, isn't random. It's directly tied to its total combinatorial value. And get this, it finds this incredible, consistent mass factor of 160,000 that separates charged leptons from their neutrinos in every single generation. It even hints at a deeper symmetry because it turns out both first-gen quarks and leptons share the exact same CV of -1. Okay, but we've got to be good scientists here and add a really important caveat. For the quarks and the charged leptons, the model's calculated values are described as being comparable to what we see in the standard model. But when it comes to neutrinos, well, that's where the author themselves acknowledges things are more speculative. And that makes sense, because in the real world, we only know the upper limits of neutrino masses. We don't know their exact values. So that part is still a theoretical proposal. And all of this really leaves us with a huge, kind of mind-bending question to chew on. This entire framework challenges a basic idea. Is mass truly fundamental? Is it something a particle just has? Or is it an emergent property? Is it something that happens when more basic pieces combine according to a deeper, more fundamental set of rules that we're only just beginning to uncover?